Hello, welcome to the series of Friday's Talk on Rust. My name is Anand Geda. I am working in the embedded system since last more than 5 years. Currently, I am working with Bosch and I am exploring embedded Rust to build security components for the Bosch. Today's topic is Berkeley's packet filter, how we can write Berkeley's packet filter using Rust, using IA library. Also, we're gonna see at the end how we can create a simple firewall using eBPF in Rust. So eBPF is nothing but an extended Berkeley's packet filter. This extended Berkeley packet filter is an highly flexible and efficient virtual machine kind of construct in Linux kernel, which allows us to execute our sandboxed programs on various hook points. These hook points are nothing but events and this eBPF program is an event-driven program. These events are nothing but which are triggered from the Linux kernel, and also eBPF program are able to receive pointers from user space and kernel space, so that they can communicate the information between the two worlds. Now, what are the events? Now, events can be of different type. For example, the network traffic, for example, XDP event, which we are going to demonstrate today. So these are the any kind of uh, packet exchange over the network, though that comes under network traffic. Now another thing is function calls. Now function calls can be of kernel space function and user space function. So K probes and U probes. Then there is another type of event that is Linux security module hooks. We can write our sandboxed code for these actions for these trigger points as well. So today's talk, in the today's talk, we are going to concentrate on this XDP ingress traffic on our network card. So what is an eBPF project layout? eBPF project layout consists of mainly two components, that is kernel space component and a user space component. Kernel space component is attached on a particular events or hook points. These events are nothing but what we have discussed previously. And user space program is responsible for loading the kernel space program and interacting with them. Also, user space program checks checks the kernel space program so that it does not have any infinite loops, and it should be short and precise. We cannot exceed the kernel space code for more than 1 million instructions. So that care has to be taken while writing our kernel space component. Now, what is an no, BPF maps? Now, as I mentioned, there are two components, kernel space and user space component. So there must be a method, a way of sharing data between these two components. So BPF maps is nothing but a way of sharing data between eBPF programs, that is kernel space and user space program. Different types of maps are hash maps, arrays, ring buffers, and perf buffers. This is a diagram which shows how the BPF map is being accessible to our user space components and our kernel space component. So BPF map is nothing but a key value store here, which is accessible to process 1, process 2 in the user space, and which is also being used by BPF program A, B, and C respectively. Now, examples of eBPF project are Cilium, that is Kubernetes networking and service mesh. Cilium, I've made some notes about that. So Cilium is it it is a project providing networking and security observability for the cloud native environment. Similarly, Tracy is an application tracing tool, and Falco is a security monitoring for containers. So as you can see, the majorly the cloud projects are being using eBPF technology. Some examples of eBPF project in Rust. So there is a BPFD, that is daemon for managing XDP programs for network filtering, and Pulsar. is a runtime observability tool for IoT domain. But we are currently exploring this Pulsar project, and Pulsar uses Aya library to build on top of that. So Aya is nothing but is a library written for writing um, eBPF programs in Rust. So in Aya, everything is in Rust. That is, our kernel component is also written in Rust, and our user space component is also written in Rust. This is a typical Aya project structure. Now, this is very interesting. So here we have, let's say, suppose the name of program is Firewall. So we have Firewall, then we have Firewall common, and we have Firewall eBPF. So Firewall eBPF is nothing but our kernel space component, which is a no standard component, and there are some dependencies and Rust toolchain to make sure that Rust toolchain.toml to make sure that our toolchain is installed properly. Then this firewall is our user space component. Now this is a standard component, and it is responsible for loading this kernel component, and also to get the response from the kernel component whenever the event is being triggered. And firewall common is the bridge between the two components. So whatever data structures or whatever arrays or key value storage or key value kind of things are there. So all the data structure which is being accessible from our user space and kernel space, that comes in our common section. And they have written some X task also to compile and to run the whole project. So this is an overall structure of Aya library. We will see how we can write this Aya, or how this thing can be used to write a BPF program from scratch. So in order to start with Aya, we need a nightly toolchain, and we need this BPF linker which can be installed using cargo install BPF linker. And cargo generate is nothing but a tool to generate a template of a program. So let's look at the demonstration now. So for the demonstration, I have created this project using Aya library. So the simple way to create a project from Aya is this command. I'll show you. I'll just increase the size so that it is easily visible. I think now it's visible. So yeah, we need to clone cargo generate. Yeah, this is the command to generate the project with Aya template. It will ask you for the project name. For example, you give here name Firewall. Then it will ask you the type of the project which you want to create. So these are all the Aya project types. So as we are talking about XDP today, so we're going to create the XDP project. Now, as you can see, our XDP project is ready. We can go to this project and start coding here. So I have already created the code here in my repository. So this is my app, and as you can see, it is exactly the project structure which we have talked about. So this is the kernel component, and if we see the cargo.toml, and so it has the dependency of Aya library, Aya BPF, and Aya logging library, and of course the common app and network types. Then if we come to the main part, so here it's a no standard thing, no main, no standard, because this is the kernel component. We start our code from here by defining or by decorating this function with this macro, that is XDP, which tells kernel that this is the hook point, or this is the trigger point. So whenever XDP traffic comes in or goes out, this function will be triggered XDP firewall, and it will have the context of XDP context. So this is the input to the function XDP context. This will come from the kernel side, and it returns a U32 for us. So here what we are doing, we are just calling one another function that is try XDP firewall. Now try XDP firewall is another function defined here, which in which we get the context. We get the Ethernet header out of the context using our another pointer at function. This is our inbuilt function. We have not an inbuilt function, our own defined function. This function we are writing to get the particular value out of this context pointer. So since this context is just the kernel pointer which kernel have provided us, we are getting Ethernet header out of it with offset 0. Once we get the Ethernet header, we check whether it is IPv4 or any other. Currently, we are just worrying about IPv4. Then once we get the Ethernet header, then we calculate the IPv4 address from it. Once we get the IPv4 address, then we get the source address from it. And finally, we check here if our source address is part of our blocked IP list or not. Now this block IP is nothing but it checks this block list is a hash map. Now this hash map is coming. This hash map is defined here, but a user space program is adding an entry to this hash map. We'll see how. So currently, what our program is doing, it is checking whether the source IP is the part of this block list. If it is, then it will drop the packet. Otherwise, it will pass the packet. And this is just the info we are printing on the console. So this is an overall or maybe very over like what we can say an outer skeleton of an XDP or IA XDP program. Then we go to user space code, and if we go to user space code here, our dependencies are again IA library, logging library. We are using clap to access the interface, uh, that is Ethernet interface here. And yeah, common as I mentioned, the common app is to be accessible to our user space as well as the kernel space. So let's walk through this user space program. Our main function starts here, and it's a async main function. So here we initialize the logger. Then we load the kernel source code. So from here we get uh, the compiled kernel code into the BPF. We initialize the logger, and then finally we create the BPF or the program out of it. And finally here we are loading the program, and we are attaching the program to this particular interface. That is what the user will provide. That is we will provide once we run this program, because we have different interfaces, right? Then here we are initializing our block list, that is a hash map, as we have discussed. So this block list is being, we are adding the value to this block list from our user space program here, and here we are adding this IP address 10.171.234.13. This IP address will be blocked by the once we load this kernel program. So we'll start compiling the code. We open a terminal, and here is our command to build the kernel side component. So what we will do in the kernel side component, currently we will not block anything. I'll just comment this out, and action is XDP pass for all the IP addresses. Doesn't matter anything, whatever IP address will be. Now the kernel code is compiled here, and we will include this kernel code with this command. We are adding this rust log flag because we want to see the info, whatever we are printing here, the kernel info. That's why we are adding that kernel flag. And this iface name is I have taken from my ifconfig command. So this is my interface name. So let's insert the kernel space component. Okay, it will take some time and it will ask for the password or the root privileges maybe. We'll open a terminal and we'll try to ping an IP address. Okay, let's wait for the thing to be getting compiled. Okay, so now here we can, as you can see, till it compiles, we can ping this IP address. That is whatever we have defined here. The IP address is 10.171, 10.171 dot, okay, 10.171.234.13. So as you can see, it is pinging. I'll stop this. What happened with this authentication service cannot retrieve authentication info. Okay, we'll again try to build this and add it into the kernel source. I think it is asking for the password. Okay, it started now. So as you can see, this it is all try. It is giving us information of all the sources, all the source IP address, and what action it is taking. So here currently it is just taking action 2. Action 2 is nothing but XDB pass because we have commented out this source code. And here also we will be able to ping the IP address. So we are able to ping the IP address 10.171.234.13. Okay. This is just the test IP address. I have taken it from some random website. So currently we are able to ping the IP address. Now we will enable this our filter and we'll see what happens. So now what happens if the blocked IP address, this IP address will be blocked now. So we'll see how that things turns out. So first we'll build the kernel component that is built, and now the user space component is also built. And now if we try to ping this, so currently it is pinging. Let's wait for insertion of our kernel space component. Yeah, it's inserted, and as you can see here, our ping operation have been stopped here after 21 pings. And here you can see this particular IP address is been blocked, and the action is one. Action 1 is nothing but XDP drop. So we will not be able to access the website on which this or which is being hosted by this IP address, which is being hosted on this IP address. So in this way we can create a very simple firewall using eBPF. Now I'll stop this program here, and you can see again we have started. The ping operation is being started here. So this gives us an idea of the lifespan of our eBPF program also. So once our user space component here, this is our user space component. Once this ends, this main function ends, our firewall or our kernel space component also ends here. There are some ways to extend the lifespan of our firewall or the kernel space code which we have added. It has to be it has to do something with the tail calls, and there are some other ways also to increase the lifespan of our kernel space component. So that's it, I guess, for this session. If you have any doubts, you can add in the comment section, or you can directly get in touch with me on LinkedIn or on GitHub. I will push this code on my repository as well as a demonstration of eBPF with Rust. And thank you very much for being there.